Alrighty, so the B one, which, like I said, is the one I wrapped in the wrong quadrant. The sine of 5 pi over 3, so 1 2/3 pi, 1 2/3. I don't know why I was graphing 1 1/3 yesterday, I just was. Looks like this. And then we realize, well, this leaves us with 1 pi over 3 short over here. And pi over 3 is 60 degrees. So this will be our negative square root of 3. This will be our 1 because it'll be opposite the 30-degree angle, and this will be our 2. So the sine of 5 pi over 3 would be opposite over hypotenuse. So this is really negative square root of 3 over 2. So what we're really trying to find now, because we always use parentheses innermost out, is we want to know where can we find that inverse cosine that would give us negative square root of 3 over 2. Now, cosine's PVR up here. We need it to be negative. Is that quadrant 1 or quadrant 2? Quadrant 2. We put it up here, and we think, okay, cosine is adjacent over hypotenuse. So I'm going to need this to be a negative square root of 3, which makes perfect sense because I'm going to the left. And then I'm going to need that to be a 2. Oh, that's the stuff in the 30, 60, 90. So that's going to be a 1 right there. And if this is a 1, what's this little angle? 30. 30 degrees in radians. Pi over 6. But now, because it's cosine, we have to name it from 0. So we're not 6 pi over 6, because that would be the whole way. We're subtracting 1 out of that. And that gives us the 5 pi over 6. Alrighty, just short of the quadrantal one here. Oh my goodness, is that the one you asked for in the homework? It's very similar if it's not exactly the same. So we've got cosine of pi. So again, I think, well, 1 pi right over here, negative 1, 0. Okay, well, it's always cosine, comma, sine. So the cosine is negative 1. So now we need to find, because we already know the cosine of pi is negative 1, the inverse tangent of negative 1. So think PVR, tangent, first and fourth quadrant. Where are we going to find it negative? Fourth quadrant. And here's our little angle, theta, x, whatever you want to call it there. And tangent is opposite over adjacent. So we need 1s, but one of them needs to be negative, which makes perfect sense in this quadrant because we're going to the right and then we're going down. So what's that little angle right there? Pi over 4, and again, with tangent, we have to swing up and down for the names. So negative pi over 4. There we go. In the 45, 45, 90s, you have two sides that are the same length. If you ignore the negative here, this is 1, 1, and then the hypotenuse is multiplied by the square root of 2 from whatever the sides is. Once I located the quadrant, I just thought through which one has to be positive and which one has to be negative. I have to go to the right. That has to be positive. I have to go down. That has to be negative. So when I saw the negative 1, I guess I shouldn't have skipped this step. I was thinking right away about negative 1 over 1 because it was tangent. And if it's negative 1 over 1, it doesn't matter if the negative is on the top or on the bottom. It just matters that there's a negative somewhere. Just 1. All right. This little bugger. Inverse sine of negative square root of 3 over 2. So let's think about that PVR for sine. For sine, we're going to be in first or fourth quadrant. Which one should this be in? Fourth, it's negative. Got my little angle right here. Like I said, theta x. It doesn't make any difference what you call it, but there it is. And I need the sine of that to be negative square root of 3 over 2. Well, that's opposite over hypotenuse, and that fits perfectly because to the right would be positive 2 and down would be negative 3. So, whoops. Said hypotenuse, and I put it on the x-axis there. So now, they're asking us what that angle is. Well, once we had this negative square root of 3 here, didn't we know what this was? What is this? 60 degrees. So we're doing pi over 3. So now, this part is pi over 3. And now they want us to find the cotangent. Well, if we just put our little 1 right here, we can just use that very drawing to get what we need.
Isn't it a negative pi? Or does that not matter?
Let me put the negative up there. Skip that, shouldn't have skipped it. Because we can use this very same drawing right here to find the cotangent. Thank you, Art. All right, cotangent. What sides do we use?
So if it was positive, you have to put that on the top one.
Yes, we should. Cotangent is what? Adjacent over opposite. So 1 over the negative square root of 3. What are you simplifying that in your head already? Yeah. So 1 over negative square root of 3 multiplied by the square root of 3 on the top and the bottom. And there's our answer. Negative square root of 3 over 3. Because this doesn't say inverse cotangent, I know there's a lot to keep track of. When you're working with the inverse functions, you have to be in the PBR, but when you're working with normal functions, we can be anywhere. Yeah, but good question, really good question. All right, talking about a quadrantal this time. If we go all the way around 2 pi, we're right back here. So if they want sine, we're just going to go ahead and say, hey, this is 1, 0. Sine is 0. So they want to know the tangent of 0. Or tangent will end up being 0. Well, tangent is y over x. So we need to find a spot where y is 0, or we can use tangent. Right up there looks like a good spot, because what are the coordinates for that spot? Well, that's not going to work, because that'll be 1 over 0. How about over here? What are the coordinates for this spot? Well, we've got a 0 here. So which one do we use? Well, this one did not have an inverse tangent there. So technically, to get that 0, we could be either here at 0, or we could be back here at negative pi. And let's put the 0 down. Sine of 2 pi, so it gives us 0. Because at this point, they didn't have us start writing formulas, but we could get a 0 here, and we could get a 0 here as we go through that. So we could put our negative, our pi for that one as well. And that's part of what you're going to see, like I said, when we go over the ones you asked about, 43 to 46. We've got a couple of spots. And this has nothing about inverses in it, so we are not staying in the PBR. This problem did not have inverses in it. Letter F. Tangent of pi. Didn't we just talk about that? Tangent of pi, we're out here at negative 1, 0. Y over x, it's 0. So we have to think, where can we get secant to be 0? What do you flip to get secant? Cosine. So getting secant to be 0, where is that going to happen? That's what we're gonna figure out. Where's it gonna be? The one out there? How about up here? So that one ends up being 1. We're going to get 1 over 1. Secant, 1 over cosine. Cosine of 0 is 1. 1 over 1 is 1. Oh, we got it. How about G? Inverse sine has to be 0. Now this is PBR stuff here. We have inverse sine. So for sine, think about these 3. It's got to be special. It has to be one of the quadrantals. Where are we going to have sine be 0? At 0. Right here. So that's at 0 degrees. So they want to know inverse cosine of 0. Well, inverse cosine is up here. So which of these 3 is going to give us a cosine of 0? And what's the name of that? Pi over 2. There we go. H is a lot like one you asked for from the homework. Remember, innermost parentheses, just follow the order of operations. So let's do the inverse cosine of 1/2 first. Get an answer, multiply it by 2, and then work forwards. So, inverse cosine 0.5, don't think of it as 0.5. Immediately change it to 1/2 because these should be things we can recognize. So inverse cosine of 1/2. Cosine has to be positive. Which quadrant do we use for the PBR when we want to have a positive cosine? First quadrant. There it is. And we want cosine to be 1/2. So adjacent over hypotenuse. And hopefully we recognize those and say, oh, that's the square root of 3 out there. So what's my little angle that I'm working towards? Because that's what inverse cosine is for, is to find angles. What's that angle? Pi over 3, because that's our 60 degrees. But now we're supposed to multiply it by a 2. Because that's what that 2 is doing in front of there. So it says 2 pi over 3. And now we need the sine of 2 pi over 3. And this can be anywhere, remember, because this is just sine. This is not PBR stuff. So 2 pi over 3, we're going over here, 2/3 of the way. So we want the sine of 2 pi over 3. What is this little angle right here? 60. We can set up our triangle, and remember, well, opposite that's going to be the square root of 3. The hypotenuse is going to be 2. So this is going to be a little -1 right here. And then we'll find the sine of it. Opposite over hypotenuse. Square root of 3 over 2. So they're getting to be little puzzles. You know, there's little pieces that we have to put together to get everything that they want. And when you look at I, seriously, 3 of them? Well, yeah. You know, it's just innermost parentheses and work your way out. So we start with, we need the sine of 3 pi over 2. It would be special because it's quadrantal. Which one of those 2 is the sine? The -1. Yeah, it's just like alphabetically. C before S, X before Y, 0 before -1. So what they're really asking us to do here is use this -1 for arctangent. Next. That's the next piece we're supposed to do. And then we'll do the secant whenever we get. I don't want to leave that off of there, but I want everybody to focus on innermost parentheses. So tangent, inverse tangent of -1. Now we're in the PBR. We don't have any choice. We're in the PBR. So for tangent, if it's -1, should we be using quadrant 1 or quadrant 4? Quadrant 4. How are you going to get the -1? What kind of triangle? 45, 45, 90. So remember, we're in the PBR. Let's give that a name. What's the name of that angle? -pi/4. And we're not done, because they had one more trig function they wanted us to get, and that's the secant. Well, the good news is we already have the drawing. We just need to slap a square root of 2 here, because we're already at -pi/4, and we need secant. How do you get secant again? Flipping cosine. Okay, so yep, and that'll be hypotenuse over adjacent. So square root of 2 over 1. And there it is, the square root of 2. All right, so we have a lot of little puzzles here with trigonometry. And you have to keep track of the fact that if you are talking about any of the inverse functions, you're in the PBR. But any of the other functions, we're all over the place. And like I said, that's something we'll throw in at the end here if we have time in the homework, where they're trying to get you to understand that by restricting what we're working with right now, that's not always going to work. Sine, cosine, and tangent go on forever. So now we're going to start talking a little bit about composition, not as much as your book had in section 4.6 that we skipped, but a little bit of it. Here's what it says: compose each of the 6 basic trig functions with an inverse sine of x. Not a value that we've looked at, it's algebra. And reduce the composite function to an algebraic expression involving no trig functions. Okay, let's start here. In order for me to use this on my drawing, I have to understand what sine is and what fraction I could use to represent it. It's the ratio of 2 sides of a triangle. Well, then I need the other side. If it just came out to be x, it must have been x over 1. It had to be. So that means, as I look at theta, my opposite is supposed to be x, and my hypotenuse is supposed to be 1. We're going to get algebra for these answers. We're not going to get numbers. We're not going to get radians. We're going to get algebra. So the first thing I think is, well, I can figure out this side. That's a right angle right there. But the Pythagorean theorem helps us find any side or the hypotenuse. I don't want to label it y because it's not y. Maybe I'll just use an a here to find it. Because I need that side if I'm going to talk about all of the other functions along with this. So a squared plus x squared has to equal 1 squared. And that means that a squared is going to equal 1 minus x squared. And when I take the square root to figure out what a is, I get the square root of 1 minus x squared. Yes, it's ugly, but we're just going to write some ratios. Because they just want the ratios of these functions. Compose each of the 6 basic trig functions with inverse sine and reduce the composite function to an algebraic expression involving no trig functions. Algebra, that's what we're supposed to do. So, they want us to do this. They want us to take what we know from this picture and use it to make composites. So how we're going to start all of these is by this. But then each time we do this, we're going to change which function we put out in front. So let's just do this in the SOHCAHTOA order that we know. Let's do the sine of the inverse sine. That's the first composition we're going to do. Well, the good news is, this is our picture. That's how we got this, was this inverse sine. So if we go back and we do the composition, we realize that's in first quadrant. They're inverses of each other. The answer to that is x. Or you go back to the picture and you say, oh yeah, sine, opposite over hypotenuse. Oh, that was silly of me. It's x. Of course it is. And we use it again. but this time with cosine. Our triangle is already built to give us that inverse sine of x. So really all we do is go back to our triangle and say, okay, what would cosine? Well, that's going to be adjacent, our nasty little square root of 1 minus x squared over 1. So the square root of 1 minus x squared. And we want to compose it with tangent. What would we get for tangent? Isn't that pretty, right? X over the square root of 1 minus x squared. Remember, we built our triangle based on the fact that the inverse sine had to be x. They said we have to do all 6, but what do we do with these 3, the last 6? Just flip them, that's it. So it'll take a little while to write them and have the notation correct, but we already know what they're going to be. Sorry, Holly? We don't rationalize the denominator with these. And here's where, yeah, the book's kind of all over the place on this. For any of our special angles, we're expected to do it for the 30-60-90, the 45-45-90. But when we leave that and we don't know what the angles are, then the book just says, leave it. That's it. Don't worry about rationalizing the denominator. Like I said, the notation took the longest time for that, right? So the picture, really, really important. If we can get the picture, we can answer whatever they want. So one of the things that I want to point out to you is this. If we need a side, we're always going to have subtraction down here. And that's because when you use the formula a squared plus b squared equals c squared, and you have to solve it for one of these two sides, you're going to have to subtract and move one of them over. But if we're looking for the hypotenuse, we shouldn't encounter subtraction, and that's because what we'll do is we'll have these numbers already here, and that's addition. So if we need a side, then we're going to encounter subtraction. If we need the hypotenuse, we're going to see addition. So let's go down here and see what happens with these. Write the following as an algebraic expression. It should be algebraic expression. Inverse tangent. We allowed to go all over this thing? Nope. Inverse tangent PVR is first and fourth quadrant. That x, is it positive or negative? So we first or fourth? First. I need to make this a little bigger so you can see. We want the inverse tangent to be x. What's tangent again? Opposite over adjacent. So again, it's going to have to be an x over 1 to make that work. And the next thing they want me to do is figure out cosine. Well, if I need cosine, I need to know what this is. So we use the Pythagorean theorem and we say, all right, 1 squared plus x squared has to equal, I'll just use c squared so it looks like it's the Pythagorean theorem. And that's going to be x squared plus 1 or 1 plus x squared. The book actually writes it both ways, which is kind of weird. But we don't have c yet until we take the square root. Now normally if we take the square root, we know we have to do plus or minus, but we're talking about the side lengths and the hypotenuse of triangles. It's not going to be negative. We don't have to do that piece. But this will give us the square root of x squared plus 1. And notice it's addition because we were trying to figure out what the hypotenuse was. Now we need the cosine of that. we've got it all right there. It's as easy as just looking at it and saying, okay, that means I need adjacent over hypotenuse. This is 1 over the square root of x squared plus 1. So building our triangle, incredibly important. Once we have that built, then the rest of it will just be fine. So let's go to B. The inverse cosine is 2x. Do we go all over the place for inverse cosine? No. Which quadrants? 1 and 2. So which one should this go in? 1. Since we don't know what x is, we see it up there. It's positive. So we need that cosine to end up being 2x. Well, it'd have to be 2x over 1. So adjacent over hypotenuse. Okay. Well, if we're going to tell them about sine, we need to know what the opposite side is. So I'll do a squared plus, and don't forget to use parentheses here, 2x plus the entire quantity squared equals 1 squared. So if we forget that, that's going to throw everything out of whack. So a squared plus 4x squared equals 1. We'd subtract the 4x squared. Then how do you undo squaring? Square root. And it's a really obnoxious square root of 1 minus 4x squared. But then the rest of it is easy because the picture's right there. You just go up and look and you say, okay, sine. I need opposite over hypotenuse. That's going to be the square root of 1 minus 4x squared. So the building is it. I mean, after that, it's just, can you do Sofitel? Do you know how to do Sofitel? Alrighty. I have to steal this to get another page. So everybody can see. Inverse cosine, PBR. Well, it's x squared. It's definitely going to be positive no matter what they put in there. But my cosine has to come out to be x squared. Well, it has to be x squared over 1. That's the only way that would happen. So adjacent over hypotenuse. Again, if we're going to talk to them about cotangent, anything to do with sine, we're going to have to figure out what that other side is. So carefully, we say to ourselves, it's going to have to be x squared squared plus a squared equals 1 squared. Well, that's x to the 4th. We're going to have to subtract that x to the 4th from both sides and square root. Now it's all right there, except this one says cotangent squared. Can we simplify that? We can't because 1 minus x to the 4th would have to be a perfect square in order for us to do that. And if you factor 1 minus x to the 4th, you get 1 plus x squared and 1 minus x squared. So it's not a perfect square. So we can't do anything more with that but no question. All right, we've got all that. Now, it says find the cotangent, and then we have to square it. So how do you get cotangent again? How do you get cotangent? Adjacent over opposite. Ooh, yuck. All right, this. Squared. So, we get an x to the 4th on the top. But there is some good news. By squaring it, we now have that 1 minus x to the 4th on the bottom. And no, we cannot cancel out those x to the 4ths. Remember, canceling is a form of division. We have to see pure multiplication to divide. There is subtraction here. So this will just be x to the 4th over 1 minus x to the 4th. now they're going to take stuff away from us. Let's see what we can do. This says, here's the answer. Work backwards and give us a composition that would make this happen. Okay. Decompose the following algebraic expressions into the composition of a trig function with an inverse trig function. Answers may vary. Whew. Well, so far we've been staying in first quadrant. I have to think square root of 1 plus x squared and an x. How could that come to be?
We don't know that.
It should be right here, because this is what happens when we have the hypotenuse. We've got that square root of 1 plus x squared going there. So we'll put on those pieces and kind of work backwards. Does it matter which of these two gets the x? I mean, I'm looking at what's squared because that's where we always get the side from. Does it make any difference? It doesn't. I'm just going to throw it over here. What did the other one have to be if that's the square root of 1 plus x squared? It had to be a 1. So we look back at what we did and we see the pattern and we realize, well, that's what has to make that happen. So now what they want us to do is come up with some way to compose this to make it work. Well, let's cheat and look what they did. If you go back, you'll notice that there was an inverse inside the parentheses to get us started, and then they had another function that gave you this answer. Well, we could do that. I think it'd be really nice to use x over 1. So that's opposite over adjacent. So which inverse should we use for that? Inverse tangent. Now, we want to get this. So we have to think which trig function would have that on the top and that on the bottom. So that'd be hypotenuse over opposite. Hypotenuse over opposite is which trig function? Cosecant. Now that's not the only way to do this composition. You actually can use their cofunctions. So if I switch this to secant and switch this to cotangent, it will. But I think that's the easiest way with all the patterns that we had when we were looking at. All right, let's look at B. Try to get a feel for what they're doing. And tell me something you know. 1's going to be the hypotenuse. How'd you know that, Cassie? Fraction. Yeah, 1's going to be the hypotenuse. Now, obviously, one of them has to be 3x, and we start thinking about which one. Again, it doesn't matter. I guess when I made mine, I put the 3x right here. What does the other one have to be? This mess. That's what it has to be. So now I think about what they did, and I realize I'd really like this to be inverse something of 3x, because that would be really nice. Inverse something of 3x. Well, 3x over 1 would do that. Opposite hypotenuse, so I'll do inverse sine of 3x. But now I'm not going to have a choice about what I use for my final answer, because they said it needs to be 3x over 1 minus 9x squared. How do you get that? Good. Tangent. So the tangent of the inverse sine of 3x. And again, you could, if you set this up backwards, you could use cotangent and cosine instead. Those are the cofunctions that will give you that. Oh my goodness, look what they did in C. This one. Well, first off, they're messing with their heads a little bit. They should look like fractions. That's what we know. They should look like fractions. All right. So 3 in front of this thing, huh? Well, we can just set up our sides and make this work if we figure out, are we talking hypotenuse or are we talking a side here? How do you know it's a side? And this time, just to switch it up a little bit, I'll put it down here. What does the other side have to be? Other side. Hypotenuse versus side. Think about where we have to get those from. Yes, we said it, but a couple people didn't even know that's not it. It's got to be the 3. Do you see why? Because we'd have 3 squared minus something squared to get us this. What's the something squared? How do you get that? 4x. We have more stuff going on. So this works, remember, because we'd have to do a squared plus b squared equals c squared. We'd have to subtract and get those pieces. Not going to be as easy as a 4x this time, but maybe a 4x over 3 would be a good place to start. So which trig function would give us the 4x over 3? Sine. So inverse sine. From that, how are we going to get the square root of 9 minus 16, x squared over 3? Cosine, adjacent over hypotenuse. Cosine. Whew. These are some good algebra mixed in. And that, in fact, that's like the least difficult thing in 12.6. In 12.6, they really go overboard, so that's the reason we skipped 12.6. This last one we're going to look at is a word problem, but we're going to turn a lot of this over to the calculator. We are. When we write this and have it all done, we'll turn it over. So it says the bottom of a 20-foot replay screen at Dodger Stadium is 45 feet above the playing field. As you move away from the wall, the angle formed changes, obviously. It's a different angle to the top. There is a distance from the wall at which the angle is the greatest, and what is that distance? Well, this is the answer they want us to find here, right here at theta. What is that greatest distance? So to do that, we're going to have to use a couple of different things. Because I can see here, I can find the whole thing. I mean, this is 65. We can get that. But I have to subtract off this other one right here. So I get started and I think, well, so far all I have is a 65 and this x and these angles here. So that's going to be opposite and adjacent. Hey, that's tangent. So the tangent of theta 1 equals 65 over x. But they asked me for the angle. So they don't want the ratio of the sides, and that means I have to use the inverse. So theta 1 is going to equal the inverse tangent of 65 over x. Theta 2, I have to subtract away because I just want that piece that's in the blue. That's all I want. So I do the same thing with theta 2, and I realize 45 over x, tangent. But I want to know what theta 2 is because that's what I have to subtract to get the blue angle. So I'm going to have to use inverse tangent. So to get what I want, I have to take theta 1 and I have to subtract theta 2. Well, this is theta 1 and this is theta 2. So I need the inverse tangent of 65 over x minus the inverse tangent of 45 over x to be my function. And yet we have not learned how to solve this yet, so we would be grabbing a calculator at this point. Actually, let me go ahead and put theta in here instead of y. So we know that we're looking for that blue angle that's up there. So the hardest part of this one would normally be the window, except the book gave us a sketch so that we could see what the window should be. And because this is in real life and most people know degrees, we want to make sure we're in degrees when we do this one. We're not talking about something in the unit circle. So let's get this in here. Second inverse tangent, 65 divided by x, minus second inverse tangent of 45 by x. And the window they have in that picture for us there, they've got the x's from 0 to 400. And then the y's from 0 to 15. They want us to know the greatest angle. Well, the greatest angle is found right here at the max, right there. So we'll put Blinky to work. Second trace, number 4, the maximum. And Blinky needs to be on the left side of the hill, so Blinky needs some elevator music for these long trips. Left side coming down, press enter. Right side coming down, press enter, and enter to yes. And there it is. So 54.083 feet approximately. Is what we could put. And that was all they wanted. They just wanted to know there's a distance from the wall at which the angle is greatest. What is that distance? And we found it. And it kind of bothers me not to put the, theta is 10.476 degrees. So I probably write that down as well. As long as we're there, we want to know what is that greatest angle that we found. So this one definitely would be one where you'd want to use whatever information they gave you to figure out your x's and y's. But the reason we got the picture was because this would be a little hard for most people to kind of envision at the ball field and exactly what's going on with that. All right. I'll make a good time to get one of those problems you asked for. Okay, let's see if we can get one of those in there. It's in the 40s. Oh, yeah, like I said, 43 would be the really good one. All right, so 2 sine of x equals 1. And I realize that even a trig function it's still like an equation. So the first thing I would do is divide by 2. And say the sine of x equals 1/2. And hopefully the bells and whistles go off and you go, wait a minute, I know that angle. I know that triangle. If sine is going to be 1/2, opposite over hypotenuse, okay, that's a 30-degree angle, which is pi over 6. It's not just at pi over 6. Because it's going to be right here at pi over 6 that we have a positive sign. But we also have a positive sign over here. And this didn't say we have to stay within 0 and 360. So we have to figure out how can we tell people every time this comes around, you're going to hit in those 2 spots. And that's where the formula comes into play. So here's what I do know. I do know that 2 pi will get me right back there. And that will be another place where they'll have a sign of 1/2. So I can put 2n pi or 2 pi n, where n is the set of integers. But it's too difficult to write a formula that has both of these at one time. So what we'd want to do is figure out where is this one. Well, like we said, we know that's pi over 6, so this would be 5 pi over 6. But again, also every time it swings around, we're gonna hit it again. Now the reason we had to do this, they didn't say find the angle between 0 and 360, find the angle between 0 and 2 pi. It was, here you go, find them all. So we had to come up with formulas to make that work. So does that help a little bit now with, because you have to do another one in, which ones? 44 and 46. Okay, so give those a try. And let me get you that one last day there. Thanks, Dave. We will get into the formula pieces that you just saw in that number 43 more in sections in the future. So this is just kind of a little starter group